Okay, let's take a look at magnesium. Magnesium is right here. You walk me through writing the electron configuration for magnesium. What would it be?
1s2.
1s2.
2s2.
2s2.
2p6.
2p, 1, 2, 3, 4, 5, 6.
3s2.
Yeah, 3s2 because we have 1, 2. Is this making sense? Okay. All right. So then what I want to do is I want to come down here into the D's. So this is 4s, this is 3d, this is 3p. Let's take a look at titanium. Okay. What do you think the electron configuration would be for titanium?
1s2.
1s2.
2s2.
2s2.
2p6.
2p6.
3s2.
3s2.
3p6.
3p6.
4s2.
4s2.
3d2.
3d2. All right? Because you go through here, 3s2, 3p, 1, 2, 3, 4, 5, 6, 4s, 1, 2, 3d, 1, 2. Okay, so that means if you were to do something that was coming out of 3D, like if you were doing germanium, germanium would be 3d10, 4p2. Okay, some online resources and textbooks will reorder the electron configuration differently. Don't pay attention to that. Do it the way that I'm doing it. This is the right way. Okay. Now, there are some exceptions to the things that I'm showing you. So in your book, we're going to highlight them, or I'm going to note them for you on this periodic table. I'm going to do that in pink. Okay, these are the ones that your book mentions as being anomalous electron configurations. So that means they don't follow the format that we are used to writing, but it's really easy to come up with what happens there. So let me explain. It is more energetically favorable for these two metals that are 4 in to the D's to have an electron jump over from the S and half fill the D. And then for these three metals, it is more favorable to have an electron jump over from the S and completely fill the D for them. Okay, so when we go to write the electron configurations for chromium as an example, chromium would actually end with 4s1, 3d5. Because an electron will jump over from 4s. Normally it's 4s2, 3d4. But that would be considered incorrect. And it will jump over and half fill the D. Okay? So you want to end these two on an S1, D5. Okay? For these here, copper is going to be another 4s1, but it will be 3d10. So copper, silver, and gold will be an S1, D10. Okay? Okay, now, what do we do when we get down here into the Fs? And then is there a shorthand version? Yes, there is. So if I ask you for the full electron configuration, you have to write it. If I ask you for the shorthand, you may write it. So I'm going to teach you the shorthand, and then we'll do these Fs. Can I erase this? Okay, so let's do the shorthand version. So this last column over here, these are the noble gases. We learned about this in a previous section, I believe. Okay, so these are the noble gases. Okay, so if I said to you, okay, I want you to write the electron configuration for gallium, but I want you to give me the shorthand version. What you're allowed to do is you write the noble gas that came before it, in a bracket, and that stands for everything up to that noble gas. So gallium has got argon as the previous noble gas, so put argon in a bracket and then write everything after it. So that means we would have 4s2, and then we would have 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you will have 4p1. So this would be the shorthand for gallium. Okay. If you happen to fall on a noble gas and I ask for the shorthand, like let's say I said, hey, give me the shorthand for argon. Great. You can just write argon in a bracket. Done. Some online resources and textbooks will tell you a different way to do this. So just make note of the way that we are doing it, because this is the way that we do it every single time. What do we do if we have an ion? Okay, so if I have something like O -2, the -2 means that we gained 2 electrons. So that means you need to move forward 2 boxes. So for oxygen, if I move forward 2 boxes, I'm writing the electron configuration for neon. Be careful, it doesn't become neon, it just has the same number of electrons as neon. So this would be 1s2, 2s2, 2p6. Okay? Yes?
In that scenario, could you shorthand neon?
If I asked for the shorthand, you could give me neon in a bracket. Okay? If we're doing a cation, if we're doing something like K plus 1, this plus 1 means I lost 1 electron. You have to go back 1 box. So if potassium is here, you need to go back 1 box, which is argon. So that means if I asked for the shorthand, you could give me argon in a bracket and you'd be fine. But if I didn't ask for the shorthand, you would have to write it all out. 1s2, 2s2, 2p6, 3s2, 3p6. Okay? If you are dealing with things that have the same number of electrons, so up here, if you were dealing with O -2 and neon, these both have the same number of electrons. So that means these are called isoelectronic substances. This is a definition in your book at the end of this section. I'll turn to that page in a second. Okay? So isoelectronic means you have the same number of electrons. So I've got 3 things left to talk to you about, and then I'm done. Okay? Okay. In terms of ions that form with, let's see, let's go for those metals. Let's go for Sn plus 4. Yeah, okay. Can I erase this? Yeah? Okay. I want to look at Sn plus 4 for a minute. If you have tin versus tin with a plus 4 charge on it, I'm going to write out the shorthand notation for you. The preceding noble gas is krypton. So this would be Kr in a bracket, followed by 5s2, 4d10, and then this is 5p2. Okay. If I have a plus 4 charge, that means I lost 4 electrons. Be careful when you're writing out the electron configuration for things that are just past the p's and their ions, okay? If it has a negative charge, you're fine, but it has a positive charge, it's like one of these weird sort of like metalloid things, that's when you need to be really careful. And the reason is because these 4 electrons that you lost are going to come out of the valence shell, which is the shell furthest from the nucleus. So that means you're actually removing the electrons that are in the 5s and the 5p because this is the valence shell. Okay, so the highest N is your valence shell. So when I remove those, technically this would become Kr in a bracket followed by 4d10. Okay. Anything else that we're missing?
What would you remove it from if it wasn't short?
Huh?
Like if
It's the same thing. Because krypton goes through 4p6. That's not the valence shell. Does that make sense? Okay. Now, how are you in terms of, are you fried? You done? Yeah.
How do we write the electron configuration for
The F's? Okay. Let's say we've got samarium. Okay. So these fit up in here. So this is 6s, 7s. This would be 4f, and this would be 5f. Okay. Let's write the shorthand. Okay. So samarium fits up here. This whole thing fits right here. So that means the preceding noble gas is xenon. So for SM, it would be xenon in a bracket, followed by 6s2. Then you go to the F's. So I have 4f, 1, 2, 3, 4, 5. If I was doing something like, I don't know, osmium, you would be doing 6s2, 4f14, and then 5d, 1, 2, 3, 4, 5, 6. Does that make sense? So the F's will precede the D's in these bottom 2 rows. Okay? All right, so the last thing that we have to talk about is orbital diagrams. So if you know electron configurations, you already know orbital diagrams. So for this, I'm going to stop the video